Hello everyone, my name is Omar Zarifi and I'm a developer at Side Effects Software. Today I'll be presenting this masterclass dedicated to the new whitewater system in Houdini17. Just to give an outline of this presentation, I'll begin by introducing the whitewater system and providing a quick overview of the major changes we've made to it in Houdini17. We'll then look at the components of the system and discuss each in a little more detail. Finally, I'll do some examples to demonstrate the new whitewater in action. So without further ado, let's begin by establishing the job of the whitewater system, which is to enhance the look of a fluid animation with secondary effects that are difficult to capture with a single simulation, such as spray, foam, and bubbles. So here we have a beach where the whitewater system was used to generate the foam on top of it with the intricate patterning. And this makes the scene look quite a bit more natural and realistic. Here's another example where splashes and spray were added on top of an ocean patch to really sell the energy of the system and the rich interactions that supposedly occur between the surface and the surrounding wind. Let's talk about the major changes we made to whitewater in Houdini17. To start off, it's a lot easier to control whitewater amount now. With the previous iteration of our system, the user had to manually specify particle counts, but given the particle counts, it was really difficult to predict how much whitewater would actually be generated when you go out to render the scene. With Houdini17, we've made it a lot more intuitive to think about the amount of whitewater, and the low-level task of managing particle counts is delegated to the solver. We've also added interparticle forces for the cohesive effect, and this endows the whitewater with much more natural fluid-like behavior, and also prevents them from clustering too closely into tight clumps. Discrete particle states and hard transitions between them have been eliminated in favor of depth-attenuated forces. So the previous system classified each particle as one of bubble, spray, or foam, and depending on the type of the particle, it would be driven by different forces. The problems occurred when particles would constantly transition between these various states as they would cross the different thresholds. With the new system, we don't suffer from this problem because all of the forces are continuously attenuated by depth, so there's no hard transitioning to cause issues. We've also added a mechanism to facilitate emergence of cellular form patterns. To this end, we've added repellents, which are special particles that are maintained by the solver, and these push nearby whitewater particles away and create the nice cellular form patterns on top of the liquid surface. Introduction of more sophisticated forces and interactions inevitably has an associated computational cost, and our improvements furthermore greatly increase the range of phenomena that can be simulated. So without any additional factors, this results in more combinations of parameters to test, as well as each combination taking longer to produce results. So to alleviate this issue, we've introduced the notion of whitewater scale that controls simulation resolution. So this enables artists to quickly iterate at the lower resolution to try out different combinations and fine-tune the various settings. And then once they're happy with the overall look, they can crank up the resolution to get some more detail out of it. Finally, we did some work on rasterization and rendering. So to this end, our default setup also generates a gradient field for density, which is an approximation of the normals. And the new basic whitewater shader uses this information to render the foam, complete with nice specular highlights that make it look a lot less flat than it did previously. So the components of the whitewater system are unchanged at a high level. You still have sourcing, which is responsible for identifying the regions within the fluid where the whitewater should appear. And should you want to manually inject particles in certain areas, you would also do so here. The source is then used by the solver to actually birth particles and perform the simulation. And this is where most of the parameters that affect emergent whitewater behavior live. Finally, the results are imported back into SOPs where the user can tweak the settings to get the geometry ready for rendering.